All right. And getting into the last part of this sort of three-part series on allergies, we're going to be talking about anaphylaxis. So this is one of my personal favorites because I have food allergies. I've had anaphylaxis. I've also treated anaphylaxis as a sort of EMT. So this is a really interesting one to talk about. So let's just get right into it. This one is going to be a little bit different than the others because we're going to be talking a little bit more about how to actually manage it clinically. We're going to be talking more about triggers on the molecular level, so talking about the actual structure of allergens. Um, and yeah, this one should be really interesting. So let's just start off by what is anaphylaxis. And you might know that generally people say it's a generalized, life-threatening hypersensitivity reaction. Um, and this is true. I would say all of those things are correct. But clinically, there's a lot of debate on what actually constitutes anaphylaxis. And again, this comes from a desire to sort of, have very clean definitions for things when in reality, symptoms and pathologies tend to present more on a spectrum or across a variety of, you know, lesser defined symptoms. Um, so, for example, some definitions that are really strict want documented mast cell and basophil release, and you can already imagine how difficult that would be in that case. But I'm going to be presenting sort of three broad definitions um, that I think capture the general gist of anaphylaxis. So let's start with the first one. This is criteria one, and it basically says if there is a sudden onset of of these symptoms that involves the skin, mucosal tissue, or both, as well as either respiratory symptoms and cardiovascular symptoms, so one or two of those. Um, then we would consider anaphylaxis. So basically, how I would say this is you need to have one of your you need to have one of your vital organ systems compromised, and then also you need to have a very rapid onset of your less vital symptoms as well. Now, the second definition is the one that I sort of ran into most in EMS, which is that they just say, oh, you need two or more body systems involved. So they don't care, this one's a little more loose than the first one because it says, well, you don't really need necessarily respiratory or blood pressure involved. You could just have, cramping abdominal pain, and you could have hives, and that would be considered anaphylaxis because it's spreading to multiple systems. So interesting to think of how, going from definition one to definition two, you really are going to start, either getting more people and classifying them as anaphylactic or getting much less people. And the final one is, you may have heard of anaphylactic shock. Well, shock is just a massive reduction in blood pressure in the body, either, because of vasodilation, plasma leakage, all sorts of things. So basically, this one's basically just saying we don't really care what's happening to your skin or your GI or your respiratory system. We just care, is your cardiovascular system in immediate danger? And if so, we're going to classify that as anaphylactic shock due to a very rapid drop in blood pressure. So something that you might not know is that anaphylaxis actually has a bunch of subtypes. You can see here that there's so many different ways that the human body can get anaphylaxis, but we're just really going to be focusing on the classic pathway, which is the IgE-mediated pathway that uses, IgE, Fc epsilon R1 cross-linking, all the stuff that we know really well already is going to be what we're focusing on. So let's talk a little bit about clinical features. So as is apparent from that definition, not all of these systems are considered to be equal by all providers. And statistically, we see that some systems are much more affected than others. So most people who have anaphylaxis, up to 90% of them, are going to have cutaneous symptoms. 70% are going to have respiratory symptoms. Half of them are going to have cardiovascular symptoms. Half are going to have GI symptoms. And then a little bit are going to have nervous symptoms as well. One thing I do want to say is that if you have a really severe anaphylaxis, and the sort of fatal anaphylaxis cases can often skip these sort of warning signs of cutaneous symptoms, respiratory symptoms, and you can just jump right into fatal shock as your sort of first clinical symptom, which is really scary. So symptoms almost always come within 30 minutes. Again, this is a very fast reaction, but there are two cases where this cannot be the case. So for delayed anaphylaxis, generally it's only ever seen in exercise-induced anaphylaxis, in which you have a very small amount of an allergen in your body, and then exercising a few hours later can move the blood around your body such that that allergen gets exposure across the body, inducing a global reaction. Or you can have alpha gal. So that occurs when the Lone Star tick bites you. So this is literally like an allergy that you get from a bug. The tick bites you, it transmits the alpha gal sugar into our bloodstream and causes you to become sensitized to red meat. And this is the primary source of like very delayed anaphylaxis. So let's talk a little bit about the molecular level of things. We have, unsurprisingly, things like PGD2, LTD4, histamine, tryptase, all of these things that we've talked about. And I would say that the main sort of function of all of these in anaphylaxis, although there are many, I would say the main is probably smooth muscle spasm. So this is what causes bronchoconstriction. This is what causes that mass spread. Vasodilation. It's what causes GI pain. But again, these also cause things like vascular permeability, vasodilation, myocardial depression. And all of these, they're listed as separate symptoms, but they really can sort of overlap and cause things. For example, vascular permeability, well, that it directly contributes to the same thing that vasodilation does, and they both contribute to the same thing that, with the same endpoint, which is just shock. So histamine is obviously the main mediator. It's derived from basophils, mast cells. And if you're interested in this, I really have a whole lecture, so I would encourage you to go there. But just to give a very, very snappy overview, acting on the H1 receptor will cause the body to respond to histamine by increasing permeability, vascular leakage, bronchoconstriction, GI contraction, mucus viscosity, which also clogs the airways. Acting on the H2 receptor brings more of the GI symptoms, as well as some cardiac symptoms like affecting cardiac contraction, things like that. But really the main function of this, the end point of this, is to just lower your blood pressure. It's going to lower your blood volume, weaken your cardiac output, weaken your contractions, and all of those things are going to lead to shock. So this one is, not sure where the image went here, but this one's really interesting. So let's talk a little bit about allergens on the molecular level. So there are some 400 known food allergens. But even though there's 400 of them, they're all comprised, they all fall into the same 71 protein families. And there are over, there's nearly 17,000 protein families. So immediately these numbers should be pretty stark, and they should tell us that there's something in these protein families that make them more likely to be allergenic. And it goes even further. If we were to take just those top 20 protein families, they account for 80% of all known allergens. So the common features that have been identified are, this sort of goes back to the food allergy lecture and topics on, barriers and getting past the gut barrier and all that. But we notice that there's a lot of proteins that aid in lipid binding, and that helps them transport into the body, transport across lipid membranes, helps them evade degradation. And the really interesting thing is, if you ever wondered, this goes back to the food allergy lecture as well, when I talked about the fact that we don't really outgrow peanut allergies nearly as much as we outgrow milk or egg allergies. Well, the reason for that is that allergenicity is inversely correlated to homology with human analogs. Now, what that means is if humans produce a protein that is relatively similar to the protein that the child is allergic to, they're more likely to outgrow it. So, for example, a child is allergic to milk, they're more likely to outgrow that milk allergy because, well, humans make milk proteins all the time. So the body's not going to be as reactive to that as it is to, say, a legume like peanuts, which has very little structural homology to humans. Another thing I want to talk about is just some other allergens. So drugs, foods, and venomous insects are very common as well. You may have heard of latex allergies. So this is a big thing a couple decades ago. And it came from the natural rubber latex material. And surprisingly, that had a lot of cross-reactivity with various fruits, which is interesting. I just thought I'd bring that up. Now, vaccines. Now, this one, almost always, you have to, after getting a vaccine, you have to wait around for them to monitor you. And this is because vaccine allergies are a real thing, but they're exceedingly rare. And very often, you're not actually reacting to the vaccine, therapeutic itself. you're reacting to the excipient, which is sort of the carrier proteins or the carrier molecules that are used to bind and stabilize the vaccine. Now, the big one is the egg protein in the flu vaccine. And so this is why a lot of people with egg allergies actually might be prohibited from taking certain vaccines as well. And then finally, physical triggers can be allergens as well, or can contribute to anaphylaxis, either by increasing gut permeability or aggravating mast cells in the immune system in other ways, as we saw in urticaria. And I thought I would just give one allergen example, so peanut, and I just want to show the scope of like how much research can be done into allergies. So this is one class of allergens out of hundreds. It's the most common, and we could say that it has sort of three main components, which is RAH1, RAH2, and RAH3. Now, all of these have several IgE binding epitopes in their amino acid sequence, but what we notice is that making point mutations in these amino acid sequences where the IgE is supposed to bind can dramatically reduce that binding affinity. So immediately we should be thinking, wow, this is like a potential therapeutic option. What if instead of trying to treat humans to make us less allergic or less reactive, we treat the actual plants and we grow them in a way that makes them less likely to bind to our immune system? That's really interesting. We also see things like RAH1 has the ability to differentiate dendritic cells, or activating them, I should say, and helps to induce Th2 differentiation, which again contributes to that allergic inflammation. However, what we also know is that if we deglycosylate RAH1, we remove that sugar, it removes the ability for the allergen to bias the Th1 Th2 balance. So again, this is really interesting. Again, like what if instead of trying to treat humans, we can also treat these plants and substances in tandem. And finally, I'm just going to talk a little bit about management. This is something that I thought is fitting to discuss because this is such an emergency that someone will likely have to go through in their life. And just being an informed bystander is really good. So if you see someone who is passed out, or they look like they're going through something, you can immediately check for medical ID jewelry. But again, if you have friends with food allergies, or you have food allergies yourself, the real best thing you can do is just to avoid all of these substances that cause those. You can also try to avoid things like beta blockers and ACE inhibitors, because those can have sort of an inhibitory response or an inhibitory effect on your body's ability to compensate for anaphylactic shock. But what I really want to hammer is that epinephrine, or an EpiPen intramuscularly, is always going to be the primary treatment for a bystander. And even in the hospital, epinephrine is sort of the main treatment for an anaphylactic reaction. So don't waste time. Give epinephrine. It's not going to hurt them by and large. And early epinephrine administration is one of the most important things in good anaphylaxis outcomes. But I do also want to say that epinephrine is not the only therapy, even though it is by far the preferred therapy. So things like supplementary oxygen can really help compensate for anaphylactic shock, where your body won't be getting nearly enough oxygen. Beta agonists like albuterol can treat bronchoconstriction that's not very responsive to epinephrine. Isotonic saline can help restore your blood pressure by just giving you more fluid. And even antihistamines can be a sort of supplementary treatment that can help some of the other symptoms. I do want to say though about antihistamines, generally if you think you're going to anaphylaxis, I'm not a doctor, but I wouldn't. I know that there is some literature that suggests that it's often not worth taking antihistamines because A, they're going to take much longer to have an effect. B, they're not going to treat the underlying causes. And C, they can actually even obscure symptoms that might be suggestive of anaphylaxis. So if you think you're going into anaphylaxis, really, really go for that first line treatment. And with that, I'll wrap up this tripartite lecture on food allergies, drug allergies, and anaphylaxis. And I hope you learned something.